The twin Voyager spacecraft stand as monuments to human curiosity and engineering brilliance, having traveled farther from Earth than any other human-made objects. Launched in the late summer of 1977, these remarkable probes embarked on what would become one of the most successful and enduring missions in space exploration history. Their journeys transformed our understanding of the outer solar system, revealing alien worlds of stunning complexity and beauty that had existed only in astronomers' imaginations until these mechanical emissaries arrived to document them. The timing of the Voyager missions took advantage of a rare celestial alignment that occurs only once every 176 years. This configuration of the outer planets allowed both spacecraft to use a technique called gravity assist, where the gravitational pull of one planet would accelerate and redirect the probe toward the next. This cosmic billiard shot meant that what would have taken decades of propulsion could be accomplished in just a few years, with each planetary encounter adding velocity and changing trajectory. Voyager 1 launched on September 5, 1977, followed by Voyager 2 on August 20, actually departing first but taking a slower, more comprehensive route through the outer solar system. The spacecraft themselves represented extraordinary feats of 1970s engineering. Each Voyager weighed about 825 kilograms and carried a suite of scientific instruments designed to study magnetic fields, charged particles, plasma waves, and of course, capture images and other data about the planets and their moons. The cameras, spectrometers, and other sensors were powered by 3 radioisotope thermoelectric generators, which converted heat from decaying plutonium-238 into electricity. These RTGs would prove critical to the mission's longevity, providing power for decades as the spacecraft ventured into the cold darkness of the outer solar system where solar panels would be useless. The computer systems aboard Voyager seem almost comically primitive by modern standards. Each spacecraft carried computers with less processing power than a basic modern calculator, using magnetic tape for data storage. Yet these systems were designed with such care and redundancy that they've continued functioning for more than 4 decades. Engineers programmed the spacecraft to be semi-autonomous, capable of making certain decisions independently since radio signals from the outer planets take hours to reach Earth. This meant the Voyagers needed to protect themselves, respond to unexpected situations, and execute complex observation sequences without real-time human intervention. When Voyager 1 reached Jupiter in March 1979, followed by Voyager 2 in July of the same year, humanity received its first close-up look at the giant planet and its retinue of moons. What the spacecraft revealed exceeded even the most optimistic predictions. Jupiter itself appeared as a roiling cauldron of atmospheric chaos, with wind speeds exceeding 400 km per hour and storm systems larger than Earth itself. The Great Red Spot, known from telescopic observations for centuries, revealed itself to be a massive anticyclonic storm with complex internal structure, its swirling clouds rising above the surrounding atmosphere. But Jupiter's atmosphere held more surprises. Voyager discovered lightning bolts more powerful than any seen on Earth, detected auroras at the poles that would dwarf terrestrial northern lights, and revealed that the famous banded structure of Jupiter's clouds represented distinct zones where material rose and fell in the planet's atmosphere, driven by internal heat and rapid rotation. The planet rotates once every 10 hours, creating fierce winds and helping to organize the cloud bands into stable patterns that persist for decades or centuries. The real revelations at Jupiter came from its moons. Before Voyager, the 4 large Galilean satellites were known mainly as points of light through telescopes. The spacecraft transformed them into distinct worlds, each with its own character and geology. Io, the innermost of the large moons, provided perhaps the greatest single surprise of the Jupiter encounter. Navigation engineer Linda Morabito, examining images meant to help track the spacecraft's position, noticed an odd umbrella-shaped protrusion at Io's edge. Upon closer examination, scientists realized they were witnessing the first active volcanic eruption ever observed beyond Earth. Io turned out to be the most volcanically active body in the entire solar system. Voyager discovered plumes of sulfur and sulfur dioxide shooting hundreds of kilometers above the surface, creating an ever-changing landscape of yellows, oranges, and reds from volcanic deposits. The source of this extraordinary activity came from tidal heating, where Jupiter's immense gravity continually squeezes and flexes Io as it orbits, generating internal friction that keeps the moon's interior molten. The discovery fundamentally changed how scientists thought about moons, revealing them not as dead, cratered remnants of the solar system's formation, but potentially active and evolving worlds. Europa, another Galilean moon, presented a completely different mystery. Voyager images showed a remarkably smooth surface crisscrossed with dark lines and featuring very few impact craters. Scientists proposed that Europa might harbor a liquid water ocean beneath an ice shell, kept liquid by tidal heating similar to that affecting Io, though less intense. The cracks and ridges in the ice might represent places where the crust had fractured and refrozen. This hypothesis would gain strength from later missions, making Europa one of the most tantalizing targets in the search for life beyond Earth. Ganymede and Callisto, the outer two large moons, showed heavily cratered surfaces more typical of ancient, geologically dead worlds. Yet even these presented surprises. Ganymede revealed areas of grooved terrain suggesting past geological activity, while both moons showed evidence of subsurface oceans based on their interaction with Jupiter's magnetic field, though these findings would come from later analysis and subsequent missions. Beyond the known moons, Voyager discovered 3 previously unknown satellites orbiting Jupiter, bringing the known total at the time to 16. The spacecraft also detected a faint ring system around Jupiter, something completely unexpected since Saturn was thought to be unique in possessing rings. Jupiter's ring turned out to be composed of small dark particles, probably dust knocked off inner moons by micrometeorite impacts. Jupiter's magnetic field proved far stronger and more extensive than anticipated. The magnetosphere, the region of space dominated by the planet's magnetic field, extends millions of kilometers into space and contains intense radiation belts that could have damaged or destroyed the spacecraft if mission planners hadn't carefully plotted trajectories to minimize exposure. This radiation environment comes from charged particles trapped in the magnetic field, spiraling along field lines and creating a hazardous zone around the planet. After the Jupiter encounters, both Voyagers continued onward to Saturn, the ring jewel of the solar system. Voyager 1 arrived in November 1980, while Voyager 2 followed in August 1981. Saturn had been observed through telescopes for centuries, its rings making it instantly recognizable, but Voyager revealed these structures in unprecedented detail. What appeared as a few distinct rings through Earth-based telescopes turned out to be thousands of individual ringlets, each a separate band of orbiting particles. The rings showed intricate structure with gaps, waves, braids, and spoke-like features that appeared and disappeared. Scientists discovered that Saturn's rings were far more dynamic than the static structures they had imagined. The particles in the rings, ranging from dust grains to house-sized boulders, interact gravitationally with each other and with Saturn's many moons. Some small moons orbit within the rings, clearing gaps through their gravitational influence. Others, called shepherd moons, orbit just outside narrow rings and help confine the ring particles to specific paths. These discoveries showed that planetary ring systems were not simple, stable structures but complex, evolving systems shaped by countless interacting forces. The composition of Saturn's rings also surprised scientists. While they had suspected the rings contained ice, Voyager confirmed they were predominantly water ice, making them highly reflective and contributing to their spectacular appearance. The ice might have come from comets, destroyed moons, or primordial material left over from Saturn's formation. The rings proved to be quite thin relative to their extent, in places only 10 meters thick while stretching hundreds of thousands of kilometers in diameter, making them proportionally thinner than a sheet of paper. Saturn's atmosphere showed its own brand of turbulence, though more muted in appearance than Jupiter's dramatic banding. Voyager detected wind speeds at the equator exceeding 1,800 kilometers per hour, faster than on any other planet. The atmosphere, composed primarily of hydrogen and helium with traces of methane, ammonia, and other compounds, displayed a pale yellow color quite different from Jupiter's colorful appearance. This difference comes partly from a high-altitude haze that obscures the deeper cloud layers. The planet's moon system proved as fascinating as Jupiter's, though in different ways. Titan, Saturn's largest moon and the second largest in the solar system, had long intrigued scientists because spectroscopic observations from Earth had revealed it possessed a substantial atmosphere. Voyager 1's trajectory was specifically designed to pass close to Titan, making it a primary target of the mission. The spacecraft discovered that Titan's atmosphere was thicker than Earth's, composed primarily of nitrogen with substantial amounts of methane. The surface remained hidden beneath an opaque orange haze created by complex organic molecules forming in the upper atmosphere. Scientists suspected that Titan might have liquid methane on its surface, creating an alien analog to Earth's water cycle with methane rain, rivers, and lakes. The Moon's surface temperature of about -179 degrees Celsius would be cold enough to freeze water as hard as rock but would allow methane to exist as a liquid. The presence of organic chemistry on Titan made it another compelling target for astrobiological interest, though it would take later missions to confirm the presence of liquid methane lakes and seas. Beyond Titan, Voyager discovered several new moons and examined previously known satellites in detail. Enceladus, a small moon only about 500 kilometers in diameter, showed a surprisingly bright surface suggesting fresh ice. Some regions appeared smooth and crater-free while others were heavily cratered, indicating different ages and suggesting recent or ongoing geological activity. This finding puzzled scientists because such a small moon should have frozen solid billions of years ago. The full explanation would have to wait for later missions, but Voyager provided the first hints that Enceladus was not the dead ice ball it should have been. Mimas, another mid-sized moon, displayed one of the most prominent impact craters in the solar system, nicknamed Herschel crater. This enormous crater spans about a third of the moon's diameter, and the impact that created it nearly shattered Mimas entirely. The moon's survival testified to either incredible luck or perhaps a degree of internal structure that allowed it to absorb the impact without fragmenting. Iapetus presented its own mystery. This moon has one hemisphere much brighter than the other, with the dark side appearing almost coal-black while the bright side reflects light brilliantly. Voyager images couldn't fully explain this dramatic dichotomy, though scientists proposed that dark material might be coating one side, either from external sources or from internal processes that had brought dark material to the surface. The mystery of Iapetus would also await future missions for fuller understanding. The variety among Saturn's moons demonstrated that these bodies had experienced diverse histories despite forming in the same region of the solar system. Some moons showed signs of past geological activity, perhaps from tidal heating or radioactive decay in their interiors. Others appeared ancient and unchanged. Some were heavily cratered, bearing the scars of billions of years of impacts, while others had surfaces that must have been renewed relatively recently in geological terms. Voyager 1's encounter with Saturn marked the end of its planetary mission. Mission planners had to choose between continuing to Uranus and Neptune or making a close approach to Titan, and they chose Titan. This trajectory sent Voyager 1 upward out of the plane of the planets, beginning its journey toward interstellar space. Voyager 2, however, continued on toward the outer ice giants, carrying humanity's observational reach to the very edges of the planetary realm. The journey to Uranus took nearly 5 years after leaving Saturn. In that time, Voyager 2 traveled more than 1.6 billion kilometers through the vast emptiness of the outer solar system, its systems aging but continuing to function. Engineers on Earth uploaded new software to optimize the camera systems for the lower light levels at Uranus, effectively teaching the spacecraft new tricks despite the primitive computing systems. They developed techniques to allow longer exposures without blurring despite the spacecraft's motion, squeezing more capability from instruments designed a decade earlier. When Voyager 2 reached Uranus in January 1986, it became the first and so far only spacecraft to visit this distant ice giant. Uranus orbits the Sun at about 2.9 billion kilometers, 19 times farther than Earth, where sunlight arrives with only 1/400th the intensity felt at home. The planet takes 84 Earth years to complete one orbit, moving slowly through the distant darkness where temperatures plunge to about -220 degrees Celsius. Uranus presented scientists with their first close look at a planet lying on its side. While most planets spin roughly upright relative to their orbital planes, Uranus rotates tilted 98 degrees, essentially rolling around the Sun like a ball. This extreme tilt means that Uranus experiences the most extreme seasons in the solar system, with each pole facing the Sun for 42 years at a time before entering 42 years of darkness. Scientists believe this peculiar orientation resulted from a massive collision with an Earth-sized object billions of years ago, an impact violent enough to knock the entire planet onto its side. The planet itself appeared disappointingly bland in Voyager's images, showing up as a featureless blue-green ball without obvious cloud bands or storms. This serene appearance came partly from a high-altitude haze of methane that gives Uranus its characteristic color by absorbing red light and reflecting blue and green wavelengths. The lack of visible cloud features also suggested that Uranus's atmosphere was much calmer than those of Jupiter and Saturn, perhaps because the planet generates less internal heat. Later observations from more sensitive telescopes would reveal more atmospheric activity, but Voyager saw a remarkably smooth world. Despite the bland atmospheric appearance, Uranus held surprises. The planet's magnetic field proved to be tilted about 60 degrees from its rotation axis and offset from the planet's center. This unexpected configuration suggested that Uranus's magnetic field might be generated not in the planet's core but in an intermediate layer, perhaps in a water-ammonia ocean under enormous pressure. The tilted, offset field creates a complex magnetosphere that wobbles as the planet rotates, creating unusual interactions with the solar wind. Voyager discovered 10 new moons orbiting Uranus, adding to the 5 already known from Earth-based observations. These moons bore names from Shakespeare and Alexander Pope rather than classical mythology, maintaining a tradition established for the previously known satellites. The moons showed a variety of surfaces and geological histories. Miranda, the smallest and innermost of the 5 large moons, provided the biggest surprise. Scientists expected Miranda to be heavily cratered and geologically dead like most small moons. Instead, Voyager images revealed one of the most bizarrely varied landscapes in the solar system. Miranda's surface appeared to be a patchwork of different terrains, with ancient heavily cratered regions adjacent to younger grooved areas with enormous cliffs and canyons. Verona Rupes, a cliff on Miranda, drops about 20 kilometers, making it perhaps 10 times deeper than the Grand Canyon. The source of Miranda's geological activity remained mysterious, though scientists proposed that tidal heating from gravitational interactions with other moons might have periodically melted parts of the interior, causing different regions to resurface at different times. The other large moons, Ariel, Umbriel, Titania, and Oberon, also showed interesting features. Ariel displayed valleys and fault scarps suggesting past tectonic activity. Umbriel appeared uniformly dark and heavily cratered, the most ancient-looking of the group. Titania and Oberon showed mixed terrain with both old and relatively young features. The variety among these moons suggested complex histories that scientists are still working to understand fully. Uranus's ring system, discovered from Earth in 1977 when the planet passed in front of a star and the rings blocked the starlight, appeared quite different from Saturn's brilliant rings. Uranus's rings are narrow, dark, and composed of larger particles than Saturn's ice-rich rings. They're so dark that they reflect only a few % of the light hitting them, making them more like chunks of charcoal than ice. 9 main rings were known before Voyager's arrival, and the spacecraft discovered 2 more, along with confirming that small shepherd moons help maintain some of the narrow rings. The encounter with Uranus demonstrated both the capabilities and limitations of the aging spacecraft. While Voyager 2 returned remarkable science despite the extreme distance and low light levels, the brief flyby meant that many questions remained unanswered. The spacecraft had only about 6 hours of close approach time to study a planet system that would take decades to fully explore. Nevertheless, the data gathered transformed Uranus from a telescopic point of light into a real world with moons, rings, and its own distinctive character. After Uranus, Voyager 2 faced its final planetary target. Neptune lay another 1.6 billion kilometers farther from the Sun, and the journey would take 3.5 years. Engineers continued to refine the spacecraft's systems, improving its ability to function in the ever-dimming sunlight. At Neptune's distance of about 4.5 billion kilometers from the Sun, sunlight is 900 times weaker than at Earth. Temperatures hover around -220 degrees Celsius, and the planet takes 165 Earth years to complete a single orbit. Neptune had not even completed one full orbit around the Sun since its discovery in 1846. Voyager 2 arrived at Neptune in August 1989, culminating a 12-year grand tour of the outer solar system. Unlike Uranus, Neptune proved to be a dynamic, active world despite being even colder and farther from the Sun. The planet's atmosphere displayed dramatic features including a great dark spot reminiscent of Jupiter's Great Red Spot, smaller storms, and bright cirrus-like clouds of methane ice. Wind speeds reached an astonishing 2,100 km per hour, the fastest recorded in the solar system, creating violent storms in an atmosphere that receives almost no energy from the distant Sun. This atmospheric activity puzzled scientists because Neptune, like Uranus, receives very little solar energy at its distance. The answer lay in internal heat. Neptune radiates about 2.6 times as much energy as it receives from the Sun, meaning the planet has a substantial internal heat source. This internal energy drives atmospheric circulation and creates the turbulent weather observed by Voyager. Why Neptune produces so much internal heat while Uranus does not remains an ongoing question in planetary science. The planets have similar sizes and compositions, yet their internal dynamics appear quite different. Neptune's magnetic field, like that of Uranus, proved to be tilted and offset from the planet's center, supporting theories that ice giant magnetic fields are generated in intermediate layers rather than in the core. The magnetosphere interacts with Neptune's largest moon Triton in complex ways, creating radio emissions and charged particle interactions that Voyager's instruments detected and measured. Triton itself became a prime target of the Neptune encounter, and it did not disappoint. This large moon orbits Neptune in a retrograde direction, opposite to the planet's rotation, suggesting it formed elsewhere in the solar system and was captured by Neptune's gravity. The capture process would have heated Triton through tidal forces as its orbit circularized, potentially melting the interior and erasing older surface features. Voyager discovered that Triton has a thin atmosphere composed primarily of nitrogen with traces of methane. Surface temperatures reach about -235 degrees Celsius, making Triton one of the coldest bodies ever measured in the solar system. Yet despite this extreme cold, Triton proved to be geologically active. Voyager images showed relatively few impact craters, indicating a young surface, and captured dark streaks that turned out to be material erupted from beneath the surface. These features represent a type of activity unlike anything seen elsewhere, a kind of cold geyser driven not by heat but perhaps by seasonal heating of nitrogen ice just below the surface. When sunlight warms this ice, even by a few degrees, nitrogen can vaporize and burst through weaknesses in the crust, carrying dark organic material upward and depositing it downwind across the icy plains. This discovery challenged assumptions about what constitutes an active world. Scientists had understood that internal heat could drive volcanism and tectonics, as seen on Io and Earth. But Triton demonstrated that even on a world far from the Sun, with minimal internal heat, surface activity could persist through entirely different mechanisms. The dark plumes rising several kilometers above Triton's surface before being swept horizontally by thin winds showed that the outer solar system still held surprises about the diversity of geological processes. The mission team had accomplished something extraordinary. Both spacecraft had survived journeys spanning more than a decade and billions of kilometers, operating far beyond their original design specifications. Every gravity assist had worked precisely as planned. Every instrument had performed through countless challenges. The images, measurements, and data returned by Voyager 2 from Neptune and Triton represented humanity's first and, as of this writing, only close-up views of this distant system. The pale blue world and its captured moon had been transformed from points of light into real places with weather, seasons, and dynamic processes shaping their surfaces and atmospheres. After the Neptune encounter, both Voyager spacecraft continued outward, leaving the realm of planets behind. Their primary missions complete, they entered what would be called the Voyager Interstellar mission, focused on studying the outer reaches of the Sun's influence and eventually crossing into interstellar space itself. Mission controllers powered down some instruments to conserve energy from the dwindling plutonium power sources, but key systems remained operational. The spacecraft continued to send data about the solar wind, cosmic rays, and the magnetic environment at the edge of the solar system. The longevity of these missions speaks volumes about the quality of their design and construction. Engineers in the 1970s built spacecraft capable of functioning for decades in the harsh environment of space, exposed to radiation, extreme temperatures, and the wear of constant operation. The attitude control systems kept the spacecraft oriented correctly. The communication systems maintained contact across billions of kilometers, their signals taking hours to reach Earth. The computers, with memory measured in kilobytes rather than gigabytes, continued executing commands and managing onboard operations. Every component had been designed with redundancy and reliability as paramount concerns, and that foresight paid dividends year after year. Throughout their journeys, the Voyager spacecraft rewrote scientific understanding of the outer solar system. Before these missions, the giant planets were known primarily through ground-based observations that could discern basic features but missed enormous amounts of detail. Jupiter's atmosphere appeared banded, but the intricate structure of its storms, the dynamics of its zones and belts, and the volcanic fury of Io remained hidden. Saturn's rings seemed beautiful but relatively simple, not the complex arrangement of thousands of ringlets with braids, spokes, and shepherding moons. Uranus and Neptune were barely more than colored dots, their tilted magnetic fields, dark spots, and active moons completely unknown. The discoveries made by Voyager transformed these worlds from abstract objects into specific places with individual characteristics and histories. Scientists learned that planetary atmospheres could be far more dynamic than Earth's, with storms larger than our entire planet persisting for centuries. They discovered that moons could be geological laboratories showcasing different processes, from tidal heating driving volcanism to cryovolcanism erupting water and other volatiles. They found that magnetic fields could be offset and tilted in unexpected ways, revealing complex interior structures. They observed ring systems of astonishing intricacy, governed by gravitational interactions that produced patterns and structures visible across thousands of kilometers. These findings had implications extending well beyond the specific worlds visited. Understanding how giant planets form and evolve helps scientists interpret observations of exoplanets orbiting other stars. Many of the first exoplanets discovered were gas giants, and questions about their composition, atmospheric structure, and migration patterns benefit from detailed knowledge of Jupiter and Saturn. The discovery of active moons with potential subsurface oceans redirected the search for life in the solar system, shifting focus from Mars alone to include Europa, Enceladus, and other icy worlds that might harbor conditions suitable for biology. The Voyager missions also demonstrated what could be achieved with careful planning, international cooperation, and sustained commitment to scientific exploration. The alignment of the outer planets that enabled the Grand Tour happens only once every 176 years. Recognizing this opportunity and acting on it required vision and dedication from scientists, engineers, and administrators who understood the value of planetary exploration. Funding had to be secured, technology developed, and teams assembled, all for missions that would take more than a decade to complete their primary objectives. The success of these missions validated that investment and inspired subsequent missions to the outer solar system. Following Voyager, other spacecraft would build on its discoveries. The Galileo mission orbited Jupiter from 1995 to 2003, studying the planet and its moons in detail and releasing a probe into Jupiter's atmosphere. Cassini orbited Saturn from 2004 to 2017, conducting extensive studies of the planet, its rings, and its moons, with particular attention to Titan and Enceladus. New Horizons flew past Pluto in 2015, extending humanity's reconnaissance of the solar system to include the Kuiper Belt. Juno has been orbiting Jupiter since 2016, investigating the planet's interior structure and polar regions. Each of these missions owes something to Voyager, which provided the initial reconnaissance and revealed where future spacecraft should look more closely. Yet despite these follow-up missions, Uranus and Neptune remain visited only by Voyager 2. No spacecraft has returned to these ice giants since those brief flybys in the 1980s. Planetary scientists have proposed missions to orbit these worlds, recognizing how much remains unknown about their interiors, atmospheres, and satellite systems. The challenges are formidable given the distances involved and the decades-long flight times required, but the scientific case for returning continues to strengthen. Voyager showed us enough to know that these worlds are fascinating and complex, but not enough to answer the deeper questions about their formation and evolution. The spacecraft themselves continue their journeys, now in interstellar space. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in August 2012. Voyager 2 followed in November 2018, providing the first direct sampling of this region from a different location and revealing variations in the boundary structure. Both spacecraft are now more than 150 astronomical units from the Sun, far beyond the orbits of all planets, moving through a region of space that no human-made object had ever reached before. The signals from Voyager take more than 20 hours to reach Earth, traveling at the speed of light across that vast distance. The power generated by their radioactive generators continues to decline, and mission controllers have been systematically shutting down heaters and non-essential systems to keep the most important instruments functioning. Current projections suggest the spacecraft will have enough power to maintain some instruments until roughly 2025 or shortly thereafter, depending on how quickly the plutonium decays and how efficiently remaining systems operate. When the power finally becomes insufficient, the spacecraft will go silent, but they will continue coasting through interstellar space indefinitely. Each spacecraft carries a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life and culture on Earth. The records include greetings in 55 languages, from various cultures and eras, natural sounds like surf and thunder and bird calls, and 116 images encoded in analog form showing Earth and its inhabitants. These records serve as messages in a bottle, launched into the cosmic ocean with the understanding that they are unlikely to be found but might persist for millions or billions of years after the civilizations that created them have passed. They represent an optimistic gesture, an attempt to communicate across unimaginable spans of time and space. The inclusion of the golden records reflects the deeper significance of the Voyager missions beyond their scientific objectives. These spacecraft represent human curiosity and the drive to explore beyond familiar boundaries. The engineers and scientists who designed and operated these missions did so knowing they were participating in something historic, pushing the boundaries of what humanity had achieved. The images and data returned by Voyager expanded human knowledge and perspective, showing us worlds we could barely imagine and revealing the solar system as a place of astonishing diversity and complexity. Looking back on the Voyager missions decades after their launches, several themes emerged that help explain their enduring significance. First, they demonstrated that robotic exploration could achieve remarkable scientific results. The spacecraft visited 4 planets, dozens of moons, and multiple ring systems, returning more data than could have been gathered through ground-based observations over centuries. The efficiency of sending robots rather than humans to these distant worlds, at least for initial reconnaissance, became undeniable. The cost and technical challenges of human spaceflight to the outer planets remain prohibitive even now, while robotic missions can be launched with current technology. Second, the missions showed the value of designing for flexibility and longevity. The Voyager spacecraft were built to last and were programmed to respond to discoveries in real time. When something unexpected appeared, like the volcanoes on Io or the structure of Saturn's rings, the mission teams could adjust observation plans to capture additional data. The spacecraft architecture included redundant systems and robust components that continued functioning year after year. This approach to design has influenced subsequent missions, emphasizing the importance of building spacecraft that can survive harsh environments and operate autonomously when communication delays make real-time control impossible. Third, Voyager illustrated how exploration can reshape scientific understanding. Many of the discoveries made by these spacecraft were completely unexpected. Scientists anticipated finding interesting features at Jupiter and Saturn, but the extent of volcanic activity on Io, the complexity of ring dynamics, and the diversity of moon surfaces exceeded predictions. At Uranus and Neptune, where expectations were lower because so little was known, nearly everything discovered came as a surprise. This pattern underscores the value of direct observation and the limitations of theoretical predictions based on incomplete data. Going to look, rather than just speculating from afar, produces insights that transform entire fields of study. The technical achievements of the Voyager missions deserve recognition alongside the scientific discoveries. Navigating spacecraft across billions of kilometers of space with sufficient precision to fly past specific moons at predetermined times required extraordinary calculation and execution. The gravity assist maneuvers had to be executed perfectly because there were no second chances. A mistake at Jupiter would have meant missing Saturn, and so on. The navigation teams calculated trajectories accounting for the gravitational influences of planets and moons, the subtle effects of solar radiation pressure, and the small forces from course correction burns. They uploaded commands across increasing distances, waiting hours for signals to arrive and return, and monitored spacecraft health through telemetry that revealed the status of systems millions or billions of kilometers away. The communication systems pushed the boundaries of technology as well. Transmitting data across interplanetary distances requires powerful antennas on both ends and sophisticated error correction to ensure data arrives intact despite the noise and interference inherent in space communication. The Deep Space Network, the collection of large radio antennas used to communicate with distant spacecraft, was essential to Voyager's success. These antennas, located in California, Spain, and Australia to provide continuous coverage as Earth rotates, received the faint signals from Voyager and transmitted commands in return. The data rates declined as distance increased, from thousands of bits per second near Jupiter to hundreds or tens of bits per second at Neptune and beyond, but the connection persisted. Image processing was another area where Voyager drove innovation. The cameras on the spacecraft captured images one line at a time, building up full frames that were then compressed and transmitted to Earth. scientists and engineers develop techniques to correct for distortions, enhance contrast, and combine multiple images to reveal features that would otherwise be lost in noise or shadow. Many of the iconic color images of the outer planets are actually composites, created by combining images taken through different filters and carefully adjusting color balance to approximate what human eyes might see. These techniques, pioneered for Voyager, have since become standard practice in planetary imaging. The cultural impact of Voyager extended beyond the scientific community. The images of Jupiter's swirling clouds, Saturn's majestic rings, and Neptune's brilliant blue atmosphere captured public imagination and reminded people of the beauty and wonder of the cosmos. These missions took place during a period when space exploration faced questions about its value and purpose. The moon landings had ended, the space shuttle was not yet operational, and budgets for NASA were declining. Voyager provided tangible returns on investment in space science, generating excitement and demonstrating that exploration could continue yielding discoveries even without human presence. Educational impacts were significant as well. The Voyager missions inspired a generation of students to pursue careers in science and engineering. Textbooks were rewritten to incorporate the discoveries. Planetariums developed programs showcasing the images and findings. Museums created exhibits explaining the missions and their significance. The excitement generated by Voyager helped sustain public interest in space exploration during a transitional period and laid groundwork for later missions. The international dimension of the Voyager missions also merits attention. While NASA led the effort, scientists from around the world participated in planning observations, analyzing data, and publishing results. The knowledge gained belonged to all humanity, not just the country that funded the missions. This spirit of international cooperation in space science has continued and expanded, with missions increasingly involving partnerships among multiple nations. The precedent set by Voyager and other missions of that era helped establish norms of data sharing and collaborative research that benefit the entire scientific community. As the Voyager spacecraft continue their journeys through interstellar space, their legacy remains secure. They accomplished everything asked of them during their primary missions and then continued operating for decades beyond, contributing to science in ways their designers could not have fully anticipated. The discoveries they made transformed understanding of the outer solar system and raised questions that will occupy scientists for generations. The images they returned changed how humanity visualizes distant worlds, turning abstract concepts into concrete places. Future historians looking back on the 20th century will recognize the Voyager missions as pivotal achievements in human exploration. These spacecraft extended human reach beyond Earth's immediate neighborhood and demonstrated that the solar system is a place of extraordinary richness and complexity. They showed that worlds billions of kilometers from Earth are not static, frozen objects but dynamic systems with weather, geology, and ongoing change. They revealed moons with volcanoes and subsurface oceans, planets with storms and complex magnetic fields, and rings with structures governed by subtle gravitational interactions. The continuing operation of the Voyager spacecraft, now traveling through the space between stars, serves as an ongoing reminder of what careful engineering and sustained commitment can achieve. These machines, built with 1970s technology, have outlasted most of the equipment that was contemporary with them on Earth. They've survived radiation, temperature extremes, and the gradual degradation that comes with age, all while maintaining enough functionality to send back data from the edge of the solar system and beyond. When they finally fall silent, they will drift through the galaxy as emissaries from Earth, carrying their golden records as messages that may never be read but stand as testaments to the human spirit of exploration and curiosity. The Voyager missions represent more than just scientific achievement. They embody the drive to explore, to seek knowledge beyond what is immediately visible or easily accessible. They demonstrate that humans can work together to accomplish goals that span decades and require sustained effort, creativity, and dedication. They show that the universe is vastly more interesting and complex than anyone imagined before seeing it up close. And they remind us that exploration continues, that there are always more questions to answer, more worlds to visit, and more discoveries waiting beyond the edge of the known. As long as the spacecraft continue transmitting, scientists will analyze their data, extracting insights about the interstellar medium and the boundary between the Sun's influence and the rest of the galaxy. When the transmitters finally fall silent because there's no longer enough power to operate them, the the spacecraft will continue their journeys in silence, moving through space at tens of thousands of kilometers per hour on paths that will carry them past other stars tens of thousands of years from now. They will become interstellar travelers in the most literal sense, having left their system of origin to wander the galaxy. The story of Voyager is a story of human ambition and capability. It's about recognizing opportunities and acting on them, about solving complex problems through ingenuity and persistence, and about the rewards that come from pushing boundaries and venturing into the unknown. The mission succeeded because talented people worked together toward common goals, because they planned carefully but also adapted when circumstances changed, and because they built systems robust enough to survive years of operation in harsh conditions. Every image returned by Voyager, every measurement of a magnetic field or atmospheric composition, every observation of a moon or ring structure represents a question answered and new questions raised. The grand tour of the outer planets transformed vague ideas about distant worlds into detailed knowledge, but that knowledge revealed how much more there is to learn. Scientists now know that Io has hundreds of volcanoes, but they still work to understand the details of its interior and the exact mechanisms driving such intense activity. They know Europa has a subsurface ocean, but they don't know its depth or composition or whether it harbors life. They know Saturn's rings contain intricate structures, but the processes maintaining those structures over long timescales remain subjects of active research. The legacy of Voyager lives on in the missions that followed and those being planned. Each new spacecraft to the outer solar system benefits from what Voyager discovered, using that knowledge to plan more targeted observations and to ask more sophisticated questions. The progression from reconnaissance to detailed study to comprehensive understanding represents the natural evolution of scientific exploration, and Voyager's grand tour was the essential first step. Without those initial flybys, scientists would still be working with incomplete models and uncertain predictions. With them, they can build more accurate theories and design missions to test specific hypotheses. In a broader sense, the Voyager missions remind us that some achievements require patience and long-term commitment. The missions took years to plan and build, more than a decade to complete their primary objectives, and have now been operating for nearly half a century. The scientists who proposed these missions in the 1960s and early 1970s spent their careers working with the data that came back. Graduate students who analyzed Voyager data during the encounters became professors who trained the next generation of planetary scientists. The missions spanned careers and connected generations of researchers, all contributing to the growing body of knowledge about the solar system. The images and data from Voyager are now historical records as well as scientific data. They represent a specific moment in human history when we first saw these worlds up close. Future missions will return better images with higher resolution, more comprehensive data with improved instruments, and deeper understanding with more sophisticated analysis. But Voyager's images will always be the first, capturing these worlds as they appeared in the late 20th century and preserving those views for posterity. They document not just the planets and moons but also the state of human technology and ambition at that particular time. Looking toward the future, the Voyager missions set a standard for ambition in planetary exploration. They showed that with clever use of orbital mechanics and patient accumulation of data over many years, robotic spacecraft can visit multiple worlds and return transformative discoveries. They demonstrated that space exploration can be conducted efficiently and effectively, producing scientific returns that justify the investment. And they proved that well-designed missions can continue operating far beyond their planned lifetimes, returning unexpected bonuses that extend their value. The two spacecraft now heading in different directions through interstellar space are operating beyond any environment they were designed to measure. They're sampling the interstellar medium, detecting cosmic rays from outside the solar system, and measuring the magnetic fields and particle densities in regions where the sun's influence is minimal or absent. These measurements will continue until the power finally runs out, and then the spacecraft will continue onward in silence, carrying their golden records toward whatever the future holds. The voyages of these spacecraft parallel the journey of human knowledge itself, moving from the familiar to the unknown, from what we understand to what we're still trying to comprehend. Every discovery reveals new mysteries. Every answer prompts new questions. The process of exploration and discovery is never complete because there's always more to learn, always further to go. Voyager embodies this ongoing quest, these spacecraft that were built to explore and have never stopped, continuing their journeys decades after leaving Earth behind.
The achievement these missions represent is both technological and human.
The engineering required to build spacecraft that could survive and function for so long in such harsh conditions was formidable.
The science required to interpret the data and extract meaningful understanding was equally challenging.
But beyond the technology and science was the human element, the curiosity and determination that drove people to attempt something so ambitious, the creativity that solved countless problems along the way, and the persistence that kept the missions going year after year. These qualities, as much as any specific technical capability, made the Voyager missions possible and successful. As these spacecraft drift ever farther from the Sun, moving into the realm between stars where human presence may never extend, they carry with them the hopes and aspirations of the people who built and operated them. They represent an era of exploration when humanity reached beyond familiar surroundings to investigate distant worlds.
They document what we found there and what we learned about the solar system we inhabit.
And they continue, even now, to push boundaries and extend human knowledge into new domains. The grand tour is complete, but the journey continues, just as human exploration and curiosity continue, always seeking to know more about the universe we inhabit and our place within it.